Hello everyone and welcome to this tutorial on the QAOA algorithm. My name is Hossein Sadeghi, and in this session I will review the concept of optimization, especially in the context of quantum computing. I will introduce some basic concepts such as QAOA and explore how it can be used to solve complex optimization problems. Optimization is at the heart of many real-world challenges such as scheduling, logistics, resource allocation, training neural networks, and even the design of new materials. An optimization problem is the process of finding the best solution from a very large set of possibilities, such that some rules or constraints are satisfied. Think about finding the shortest route between two cities with the constraint to use roads, or efficiently allocating resources in a factory such that resources are not overbooked. These are optimization problems, and they can become incredibly difficult as the number of choices grows. This is where the concept of NP-hard problems appears, for which finding the best solution takes an exponential amount of time in the worst-case scenario. The goal of quantum optimization is to use the power of quantum computing to solve optimization problems more efficiently than classical computers, at least for certain types of problems. Okay, now we're going to look at the maximum independence set problem as an optimization problem. Maximum independence set tries to find the largest set of nodes that are not connected to each other. So, for example, if we have a graph G with sets of nodes V and sets of edges E, the task is to find a subset or the largest subset of nodes for which no two nodes in the subset S are connected to each other. We can present this as an optimization problem by introducing the binary variable xi. If xi equals 1, it means that the vertex I is in the set S. And if xi is 0, it means it's not in the set. So if we take the sum of xi's, our goal is to maximize this sum or minimize the negative of the sum, subject to the constraint that for every edge ij, the sum xi plus xj is less than or equal 1. In algorithms like QAOA, we usually work with an unconstrained objective function, or known as quadratic unconstrained binary optimization, QAOA. In order to do that, we need to convert this constraint of inequality to a quadratic objective form. To do that, in this case, it's relatively simple. If we take the product of xi and xj and add it to the objective, we see that the product is 0 when the constraint is satisfied, and so it is inconsequential to the objective. But if they're both 1, it violates the constraint, but the product appears as a positive number in the objective. And because we are trying to minimize the objective, we are also minimizing these violations. In a more formal way, and for more complex constraints in the future, there's a way to systematically find this quadratic objective for each constraint, and I'm going to go through that now. Suppose that we express our constraint as a penalty Pij for every constraint ij. I can write that as a quadratic function. In this case, I'm assigning the same coefficient to xi and xj due to symmetry, and then I pick another quadratic term. Notice that we don't have xi squared or xj squared because for binary values, xi squared is basically xi. And we also have a constant number, which is inconsequential, but just to be complete, this is a most general quadratic form. Now, what we want is to make sure that this penalty is 0 when the constraint is satisfied, and if it's greater than 0 when it is not satisfied. So by substituting xi and xj into this equation, we get 4 possibilities. If they're both 0, we have c. If one of them is 1 and the other is 0, we get a plus c. And if they're both 1, we get 2a plus b plus c. Now, if we set 3 of the possibilities to 0, we find that both c and a are 0. And so we are just left with the term b, which we can set it to lambda. Lambda is a typical symbol for penalty, or Lagrange multiplier, which is a different concept. So here we are just left with this quadratic term, just like intuitively we thought about it. So now we can add this to the objective function and get the full QAOA formulation for a maximum independence set problem. We want to minimize this whole thing, minimize this sum, which means maximizing the number of nodes selected, however, making sure that this constraint is satisfied. Additionally, we want to convert the QAOA to Ising. The reason is that generally when we work with a quantum hardware, we're working with spin variables, two-level systems in a quantum computer, and they're usually represented as spin variables that have values -1 and +1. So we can take our QAOA expressed in terms of binary variables xi and xj and convert that to spin variables zi, which is -1 and 1. In this case, xi is expressed as y minus z divided by 2. You can check this. If z is 1, you get 0. If z is -1, you get 1. By substituting x everywhere in the objective, we arrive at this equation, which is the Ising-Hamiltonian. We can disregard this constant. What matters is that the coefficients j and h are related to the QAOA matrix. Okay, so now let's go through an example. Let's consider a simple graph with 5 nodes such that they're connected the way you see here. The QAOA for the MIS problem looks something like this. This is very trivial. We want to, again, minimize the sum, but also we want to make sure that these constraints are satisfied. All these terms are 0, meaning that, for example, x0 times x1 is 0. Because these two nodes are connected, we want the value of x to be 0 for one and 1 for the other, or the other way around. Okay, so I just plugged in the QAOA matrix here. I've introduced a few lines of codes here to calculate the energy for each possible solution. We have this function that calculates the energy or the objective of an instance. An instance is provided as a bit string, which is then turned into a list of 0 and 1s here. By going through each possible values, all 2 to the n possible values, and representing them as binary strings, we calculate the energy instance, we sort them by energy, and we print the first 5. You can see here that the lowest possible energy is -3. This means that the maximum independent set is at most size 3. And here I've visualized the solution. You can see that the best solution is when you select the nodes 0, 2, and 4. This way, this is the largest possible set of nodes that are not connected to each other. You can see that 0, 2, and 4 are not connected directly. Okay, so I'm going to define a few more functions as well. So for example, bit string to Ising, and I'm going to calculate the Ising parameters as mentioned before, and then calculate the energy using the Ising formulation. We'll just verify that these two energies are the same. So this is nothing special, we just verified that the calculation of QAOA and Ising energy are consistent. So before we move on to the QAOA algorithm, let's just clarify a few things. Because we are working with multi-qubit systems, we want to make sure that we understand how these matrix operations work. When we have 2 qubits, 0 and 1, and we have matrices A and B acting on each qubit, the overall matrix is the tensor product of these two operations or operators. So for instance, if we are working with a 2-level system, the matrices are 2 by 2, and the tensor product is 4 by 4. If we go to 3 qubits, then the size is 8 by 8. Whenever we present a single qubit operation like X or Z Pauli matrices, implicitly we mean that the operator is actually the tensor product of that operator with the identity for other qubits. So let's take a look at this example. We start with the state 0, 0, which means that qubit 0 and qubit 1 are both in state 0. And we apply the operator X on the qubit 0. This means that we are actually applying the operator X times I for qubit 0 and qubit 1, which means that X acts on the first qubit and I acts on the second qubit. I is the identity, so it doesn't do anything. X is a bit flip operator, so it negates the value of 0 to 1. And then 1 tensor product 0 just means this state 1, 0. If, for example, we wanted to apply X to both qubits, it would look something like this. We would have X tensor product X. Each one acts on the corresponding qubit, and then at the end we get the 1, 1 state. So the same is true for our cost Hamiltonian. Our cost Hamiltonian is an Ising Hamiltonian with Z and ZZ terms. Whenever we see the product of the spin I and spin j, really what it means is that we have this string of Pauli terms where everywhere we have the identity matrix except for the indices I and j. So here's an example for 4-qubit system. Z1, Z3 means that the second one and the last one are Z and the rest are identity matrices. Okay, so now let's introduce the QAOA algorithm, or quantum approximate optimization algorithm. This is a heuristic quantum algorithm. It's actually also a hybrid algorithm because it involves not just applying operators on states and getting expected values, but also optimizing parameters of this circuit using classical methods. Usually we start with an ansatz. Our ansatz here is made of a cost Hamiltonian, which we talked about. This is the problem we're trying to solve. There's a mixer Hamiltonian. The idea behind the mixer Hamiltonian is it is something that, first of all, does not commute with our cost Hamiltonian. And in principle, it can create entanglement between every possible qubits if applied long enough or enough number of times. And then we have a set of parameters that control the circuit's performance. And there's a concept of layers, meaning that we apply certain type of operations many, many times to create quantum states that are expressive enough to be able to solve our problem. So this is what the QAOA algorithm looks like. You start with the plus for all qubits. This is usually achieved by applying the Hadamard gate on the 0 state. It creates the superposition of 0 and 1 for each qubit. The product of all of them means that you have a uniform superposition of all possible bit strings. Then on this superposition, we apply these operators. So we apply this kind of QAOA layer p times. And each one is the exponential of first the cost Hamiltonian and second the mixer Hamiltonian. Note that we cannot simply combine these two exponentials into a single term because the mixer and cost Hamiltonian do not commute, and we're not allowed to express them as a single term. The cost Hamiltonian is applied with a parameter gamma, and the mixer Hamiltonian is applied with a parameter beta. And the parameters are the same for all the qubits, but they change from layer to layer. Our objective is, after evolving this initial state into this final state that depends on gamma and beta, our goal is to minimize the expected value of the cost Hamiltonian given the parameters gamma and beta. So we want to find gamma star and beta star such that this expectation value is minimized. Okay, as I mentioned, we are going to use these exponential operators, the exponential of the cost Hamiltonian. But the cost Hamiltonian itself is the sum of multiple terms that are made of single and 2-qubit Z operators. Because Z operators for different qubits commute with each other, we can actually break the exponential of the sum to the product of exponentials. So meaning that e to the hc is e to the sum over terms, but we can just take each term individually, take the exponential, and apply them one after the other in any order that we want. So this is very important. Now these terms are made of single and 2-qubit Pauli Z operations, and also the mixer Hamiltonian is Pauli X operator. The exponential term looks like this. So we have the H bias times Z. So this is the linear term of the Ising Hamiltonian times gamma and I. This exponential is the same as applying the Z rotation with the angle to gamma H. This is by definition. The RZ gate is defined as e to the minus I theta Z over 2. And so if we want to have this term, the angle is calculated this way. This is the same for the X operator, except that the rotation is around the X-axis. For the 2-qubit, we want to calculate the exponential of this 2-qubit gate operator with a coefficient J. In this case, the effect is a little more complicated. It cannot be expressed as a single rotation. There's actually a term for it. There's a gate for it defined in Qiskit. It's called RZZ. which basically performs the operation we want with the angle 2 gamma j. But let's take a closer look at this operation and see what it looks like. So suppose that I have this arbitrary state psi. Oh, there's an extra psi here. I made a mistake. Suppose that we have this arbitrary wave function, and we want to apply e to the minus I gamma j z1 z2 to this 2-qubit system. The effect of this term is that when we apply this exponential operator, basically we can replace the z values with the effect of z on each of the individual states. The reason is that these states individually are eigenstates of z1 and z2, so the effect is trivial. We just get the eigenvalue out of it. So z1 on 0 gives us 1, and z2 gives us 1 as well. So this z1, z2 becomes 1, no change. However, when we have 1, 0, one of them produces a negative 1, the other produces a 0. So in net, we get a negative here, which cancels the negative there, and we get this positive term. The same is here. 0, 1 gives us positive term, and 1, 1 gives us 1 times minus 1, which is the negative term. Now you can actually show that this is the same as applying the Cx or C naught. They are the same on our arbitrary wave function, doing a rotation around z-axis for qubit 2, and then applying another Cx gate. So let's go through this. So first I apply the Cx gate. It flips the second qubit if the first qubit is 1. So 0, 0 is unchanged, 1, 0 becomes 1, 1, 0, 1 is unchanged, and 1, 1 becomes 1, 0. Then I apply this rotation, which basically acts only on qubit 2, and the sign flips if the qubit 2 equals 1. So you can see that the first term doesn't change, the z2 becomes 1, it disappears here. The second term flips, the third term flips, and the fourth term does not change. Now we apply another Cx gate, which brings back 1, 1 to 1, 0, and 1, 0 to 1, 1. So now we are left with this state, which is exactly the same as the effect of applying e to the 2-qubit Z Pauli matrix. And therefore, these two are equivalent. Okay, so now that we know how to implement the individual terms of QAOA, we're going to construct the QAOA circuit. So first I'm going to convert the QAOA matrix to a bunch of Ising terms. This is nothing new. The Ising terms are related to the QAOA matrix and the linear terms as well. And in the end, we just return a list of terms with their coefficient, the Pauli matrix that is used, and this index of qubits that are involved. Let's look at this example, our 5-qubit independent set problem. After converting it to Ising Hamiltonian, we are left with 5 2-qubit gates and 2 single-qubit gates. The rest, 3, have a coefficient 0. All right, so now to create the QAOA circuit, first we define a quantum circuit with n qubits and also n qubit for measurement. So these are the classical bits. We break our input parameters into 2 sets. The first half will be used as gamma for the cost Hamiltonian, and the second half will be used as betas for the mixer Hamiltonian. We're going to apply a Hadamard gate on all qubits. This creates our plus qubit, plus a state for all qubits. Then for each layer, we're going to build the cost Hamiltonian first, and then the mixer Hamiltonian. So for the cost Hamiltonian, we go through each term, we pick up the coefficient, the Pauli terms, and the qubits. If we have single qubit operations, we apply the Z rotation. If we have 2-qubit gate, we apply the RZZ rotation. As an example, I also put the third order term here. If we have ZZZ, then what will happen is that kind of this similar idea to RZZ, which was C naught RZ C naught, we have C naught RZZ C naught, or it could be 2 C naughts RZ and 2 C naughts, and the same pattern continues for as many terms there are in our as many Z operators are in our term. And the mixer Hamiltonian is the same, except that we use the beta terms. And it's the same concept. We apply rotation around X on qubit K. At the end, we add measurements. Sometimes we don't need measurement because, for example, we are doing a state vector simulator, but in this tutorial, we're just going to go over a method using sampling. So let's take a look at what the circuit looks like. This is again our QAOA for the simple example. We obtain the cost terms, we construct a circuit, and this is what the circuit looks like. We had 5 qubits, Hadamard gate on each of them, 2 qubit rotations on pairs that are connected. And you can see that RZ appears only for 2 qubits because for the rest, the coefficient H is 0. And then we have Rx rotation on all the qubits. And this is just for one layer of QAOA. You can play with 2 or 3 layers and increase the number of parameters and see what the circuit looks like. So now we're just going to do a few other things before running the QAOA. So the first thing is that in Qiskit, the bit strings that are returned, the qubit 0 is at the end of the bit string. So we're going to invert it so that the first bit is the qubit 0. And this is a simple execute function which is removed in recent versions of Qiskit. Using a backend, we just run the circuit with a number of shots and other parameters and return the inverted bit strings and their counts. We also compute the energy. The energy for this counts dictionary is basically the weighted average of the energy of each instance as determined by the bit string that is returned. Here I assume that you're familiar with Qiskit already. We're going to use the air simulator. Air simulator is moved to a separate library. It's not part of Qiskit itself. And then because we also are doing parameter optimization, we're going to use Kobila method, which is relatively fast and it's gradient free. So I'm going to define the backend as Chasm simulator from air. I'm going to put everything together into a single objective that takes as input the parameters of the QAOA circuit, and it outputs the final expected energy that we want to minimize. This way, the function minimize knows what the input and outputs are. And then after running this simulation, it takes a very short amount of time. We get this information back. So this is the set of optimized parameters that are found. We have QAA with 2 layers, so there are 4 parameters involved. We get an expected value of -1.5, so it's not quite -3, but it's negative, and it's potentially the best solution is in the set of samples. Okay, so now what we're going to do is we're going to take the best set of parameters that are found from our optimization and run this, create the circuit and execute it again, this time with much more samples. And then I'm going to look at some of the best solutions we found, and we see that we actually observed the best solution 25% of the time, which means that our optimization has been relatively successful. And then here I have visualized the solution. We see that we find the expected result 25% of the time, more than any other sample. Okay, so now let's look at the effect of the number of layers on the performance of the QAOA algorithm. Generally, we expect to see better performance as we increase the number of layers. It is relatively challenging because as we increase the number of layers, the circuit becomes deeper, simulating it takes longer, and also we end up with more parameters that we need to optimize. So here what I'm doing is I'm going through a range of number of layers from 1 to 6 layers. Every time I'm collecting 5,000 shots, but additionally I'm also running random circuits and optimizing each 20 times per number of layers. So in overall we have 120 experiments. So there's nothing special here. I'm simply looping over the number of layers, looping over the trials. I'm initializing theta every time, and I'm running the QAOA and minimization and obtain the and then for each instance we take the optimized parameters, run the circuit again, and then we look at the median 25 and 75 percentiles, just to get a sense of, for the 20 trials, what is the median or kind of expected success rate. And after plotting all of this, you can see that as we increase the number of QAOA layers, we generally get a better success rate. However, sometimes this doesn't follow. It's simply because we have more parameters, and it is possible for the optimization to not be successful, especially because we are using finite number of samples. Even if the algorithm reaches convergence, if you switch to exact expectations, you might see that actually the solution is not optimal and we are not even in local minima, and you can make improvements immediately. So with that, I will leave you. This notebook is linked in the video. You can go through it and play with the parameters and even run your own optimization problem as you wish. Thank you.